I'm going to switch the video. There we go. Okay. Morning, everyone. How's everyone doing? Everyone awake? Barely? So my name is Grant McAlister. I'm a senior principal engineer with Amazon Web Services. I work in our database group, and most specifically, I work on our relational database service, Amazon RDS. And I spend most of my time in that group working on the Postgres engines, which we have RDS Postgres and our new engine, Aurora Postgres. So, but this talk's not really about that today. What the talk today is about is tuning Postgres for high write workloads. And so we're going to walk through a bunch of stuff on that. So what do I mean by high write workloads? Well, for some people, this can mean I just have a single-threaded app that does inserts and updates. And in that case, the client talks to the database talks to the storage to do basically a commit, and then it's got to come back from storage, and that's your commit latency. And that's really going to affect how fast you go, as well as the return of the client and the client latency. So this is really hard to make go very fast unless you're going to tune those two things. So some of the ways around that are people start using bulk methods. You do copies, or you do multi-insert. Postgres is one of the engines that allows you basically on a single insert to insert a lot of data. So now you've got a much sort of chunkier set of data going to the database. You've got bigger log flushes going to storage, but commit latency still matters. And then you have the return to the client. And so client latency still matters. So the way around this for most things is to go and have many clients working. And whether you're doing small things or bigger things, you basically have a huge amount of clients. And this is like if you were running, let's say, PG Bench to do a benchmark, you might be running with 500 clients to get maximum throughput. So then this problem becomes less about commit latency, although it's still important, and less about client latency, as it is about throughput. So, and I'll show you why that matters later on in the talk. So to test this, to walk you through this, what I did was I built a table. And I'm just going to walk you through that real quickly. I start with the PK being a UUID. And so that's essentially a random value. I next added like a typical ID, which is a right-leaning sequence. This is what you normally would have as a PK for a lot of tables. I have a varchar 100 that's going to be all random characters. I have a varchar 50 that's a small set of words. An integer, which is a very large integer, all random. A smaller integer, which is a smaller set of randoms. A Boolean, which is random, but there's only 2 values, so that's not really that. And then a Boolean where I leaned it to one side, so it's a 75% true and a 25% false. And then a timestamp, like basically like the now function in Postgres, which is also right-leaning. And then I did the really evil thing and I indexed every one of these. And you say, well, who would do that? Well, no one would normally have 9 indexes on a table if it's only got 9 columns. But instead of building the 250 column table that many of you probably have in your databases with 9 columns indexed, I thought this was just an easier way to see it. So let's run this workload on Postgres. Here's 9.6. This was run on RDS, single AZ, so no extra. We're not replicating to another availability zone. I try to keep it simple. And it's the default parameters. And so what you get here is you see on that far left, we've got the vertical axis is transactions per second, right? And you can see that we're doing like 25,000 at the beginning. And then it drops off very quickly, right? And it's minutes along the bottom, so this is a 5-hour run. So, you get a good like 10 minutes of good performance before it all goes horrible. And really, what we want is we want something like that black line, right? We would like something doing 26,000 TPS on these inserts and not having a problem. Hang on 1 second. Let's see if I can turn my wireless off. Well, whatever. So I also wanted to show you what updates look like. So the same table, and what we're doing is an update on the Boolean, and then the second update is on the timestamp. So this is kind of a typical thing where you might be like, hey, I updated the thing, and I also wanted to have a last updated column. So this is sort of typical. So again, the base workload, doing this update, there's 2 updates per transaction. And what we see is we get around 3,700 writes per second, or updates transactions, so about 7,000 total writes done. What we really want is something more like 10,000, right? And again, what could we do to get there? Well, that's what we'll walk through. So we'll start with parameter tuning. So one of the things that I noticed right off the bat with my workload was it was checkpointing about every 5 seconds. So that's not necessarily something that you'd want to have happen, so let's start thinking about how we can change that. So I'm going to walk you through sort of how some of the concurrency works in most databases, and specifically Postgres. So let's say you have a whole bunch of clients, and they all have a whole bunch of queued work, and that's what I'm showing in that yellow. Then you have the log buffer that the database has, and you have the storage. So essentially, when you go and you queue that work up, it goes into the log buffer when you say commit. Now, that's got a flush to storage, but in the meantime, a whole bunch of the other sessions have queued up work that they would like to now commit. But they can't yet because they're blocked, because the log buffer is in the process of flushing. And so until those items get through storage and get done, you can't re-enter the log buffer. So this causes a very stop-start method, and this is where the throughput of getting through the log buffer really matters. And the larger the log buffer is, the longer it takes to write, which is the longer you're blocked from re-entering the log buffer. The other thing that's interesting with Postgres is a thing called full page writes. How many people know what full page writes is? Okay, quite a few, good. So let's say we got this block in memory, and we start doing updates and changes to it. That's going to end up in our wall, but if this is the first time we've touched that block since we last checkpointed, we're also going to get a full block or a full page write into the wall stream. So if we touch it again, since we haven't checkpointed, it's now a tiny little change, right? We have to checkpoint that block, and we have to archive that, okay? So why do we do full page writes? Well, because Postgres by default has an 8K page size. But let's say on Linux, you're actually an operating system that has 4K pages. So you end up, when you checkpoint that block out, you end up actually doing like 2 writes, and one of those may fail, let's say if the box crashes in between those. Now this is not a likely occurrence, but if it does happen, basically you have a split page or a torn page, and you have corruption. So if you didn't have the full page writes happening, you'd kind of, sooner or later, you'd find out, a month down the line that, oh, that data really isn't usable. So what Postgres does is during crash recovery basically uses these full page writes to replace those writes, those kind of incomplete checkpoint writes, so that you don't have corruption. So this is a really important thing from preventing corruption, but it does come at a cost, and we'll go through that in detail. So here's a cut down view of a dump of a wall file. Hopefully everyone can read that. I'm trying to make it as big as possible. That looks kind of okay. There's no full page writes. And then later on in my run, where you're starting to see the very slow performance, what we see is a ton of full page writes. And if you can count that, you'll see that we basically have 8 full page writes happening, right? And what that works out to being is that left side was doing 1K per insert, right? The right side is doing 48K. So I'm inserting 1 row, and it's taking 48K to go through the wall stream, right? So that's very painful. And that's why we see the performance slow down. So what could we do? Well, we could maybe turn on wall compression, right? So what that does is it helps with the size. So let's walk through again, what we've done, and you get the full block in the log. Well, if you turn on wall compression, that block in the wall stream is going to be smaller. But it might be that big, it might be a little larger. It all depends on how random the data is. So if you have lots of random values, you're going to get pretty poor compression, right? So I reran my test, and now the green line is with wall compression turned on. Doesn't look like that helped much, did it? What about on updates? Well, on updates, it helped a little bit. We got, an extra couple hundred transactions per second, which is not bad. And this is actually not typical. And the reason why was my data, again, is almost entirely random. It's not what your normal data would look like, right? So if I go look at the size of the average full page write in my wall stream, it was 5.7K. Compressed was only 5.2. So we didn't save a lot, did we? And the reason is, again, because essentially I have a fake data set, right? In the real world, what we see is we actually see wall compression actually making a significant reduction in the size of the full page writes, and it does help with performance. So again, random data does not compress well. So the next thing to do, typically, is what you want to do is you want to have longer checkpoints. Because again, you full page write after a checkpoint. So I increased the max wall size from 2 gig up to 16. We have the same chart here, and now that's the blue line of running with the larger wall size. So it looks much better at the beginning. We managed to, for almost 20 minutes get really good performance, but then we slowly slide down to almost the exact same place we were with the earlier runs. And the reason is we get more blocks, more random inserts, more full page writes. So what do I mean by that? If you assume that we're doing 10,000 updates per second, and we're checkpointing every 60 seconds, then essentially we're touching 600,000 random blocks between each checkpoint, right? If you have a 1 gig table that has 130,000 blocks in it, then most likely you're going to touch the same block multiple times, which means no full page write except for on the first time, right? But if you have a 100 gig table, you're going to have 13 million blocks. And essentially, the chance that you touch the same page twice is actually starting to get very low. So almost all of your run will be full page writes. So this is really important when you have random data. So here's what we see on the update workload. We actually did get a reasonable benefit, going up by about 30%. So it is a good improvement. Now someone would say, well, why not run async? Why you're doing this high write workload, maybe you could run async, wouldn't that help? And as you can see, it actually doesn't. It actually made things slightly worse. And here's the reason why. When we go back to this log buffer example, right? When we have that queued work and it gets into the log buffer, and we have new queued work show up, so even if we're doing async, what happens is that storage, essentially, now we don't have, those guys that are the 8 little yellow blocks there, they don't actually have to wait, right? But notice the folks up top still have to wait because they can't enter the log buffer. So it's less about the commit latency now than it is about how long it takes the log buffer to empty, right? It's about throughput. Oh, okay, fine. So when we added the extra, wall space to make our checkpoints longer, that helped our performance. But there is a downside. So I went from a min wall size of 256 meg up to 2 gig, and I went from 256 and 2 gig to 2 gig and 16 gig. But you'll see the recovery time is drastically different, right? It goes from 3 seconds to 91. You can imagine if my checkpoint was now running at like 5 minutes, then my recovery time is going to be probably much closer to that. So one of the things that you have to trade off here is in your application deciding how much downtime can I take when I do crash the database versus how much write throughput do I want, right? So we could continue sort of working on making our checkpoint more effective and larger, but I kind of wanted to leave it there so that we can see some of the other ways that you can actually get performance improvements without doing parameter changes. So let's take a typical B tree, and this is not absolutely correct, but it just kind of to show you kind of an idea here. If we insert a sequence into a B tree, right, like 201, what we're going to do is we're going to touch all those blocks, right? Now, if those blocks weren't in memory, we would have to load 4 blocks, right? Now, since it's a sequence, the next time we go to insert like 202, we basically don't have to load any more blocks, right? It's essentially free. And from a full page writes perspective, if you assume that those changes came after a checkpoint, we would only possibly have to do 1 full page write. Now let's talk about what happens if we do that to a random tree, or a random insert into that tree. So if we insert 124, what happens is we see again those typical 4 blocks that need to be loaded. But now when we do something like 99, what happens is we're starting touching more blocks again, right? So 3 blocks this time. And 161, now again, a couple more blocks. And you can see if this was an actual real representation of a really large tree, right? This would continue on pretty much with every time you're touching something, you're touching a bunch of new blocks. So this is actually important for multiple reasons. One is, if you're doing this kind of randomness, you need a lot more memory to hold your B tree in, because if those blocks aren't in memory, you're going to have to load them every time. And the other thing that you're seeing is, even if we just look at the modifications to the leaf nodes at the bottom, we had to touch 3 full page writes, as opposed to in the previous example where it's 1, right? So that's a large amount of full page writes that we're doing. So to see that in action, what I did is, remember, the table with the 9 indexes. Let's cut it down to 6. So we removed this index on a random string. We removed this index on this random integer. And we removed this index on this Boolean. Now remember, this is one of the columns that we were updating. So this allows us now to have hot updates. How many people know what hot updates are? Good. So for those that don't, I'm going to just run quickly through this. So assume that you have indexes A, B, and F, and you have a table with A through F as columns. And so you can see the indexes, they basically point to the heap, right? And if we went and modified, for example, column F, which is an indexed column, then we essentially, what we have to do in Postgres is, we create a new tuple in the heap, and then we mark the old one as old, and then we have to repoint the index to it. But that means we've got to make all those changes to the index pages as well as the heap page, right? Now this occurs if you're updating any column that has an index. It also occurs if there's not enough room in the heap for a new tuple. So in this case, even though in the second example, I'm updating C, which is not an indexed column, because there wasn't enough space, we also don't get a hot update. So in the hot example, if I go and do that same update to C, what happens is, instead of us doing a whole bunch of changes to indexes, all you end up is linkage in the heap tuple, or between the tuples in the heap. And so the indexes don't have to change. And so this is a lot less work if you can do hot updates. And to show you that in detail, here's again a slice of a wall output where I do my hot update. So I have my heap and my xlog, and you'll see 1 full page write. Because, but when I did my non-hot update one, what I see is 5 full page writes. So this is a dramatic difference on the cost of those 2 update statements, right? And again, it's basically 3.5K versus almost 17K, right? So it's a dramatic difference if you can do hot updates. So this is really important in Postgres when you're thinking about what things to index. You really want to look at what columns you're changing with update statements and really be very, kind of diligent about, do I need to have an index on that? Because it comes at a very large price if you're doing high writes. So how can you look at this? We can look at pgstat all tables, and they have 2 columns, which is basically the number of tuples updated and the number of tuples hot updated. So if I go and do my update, and here I'm updating column E, which is the one that doesn't have the index now, what we see is that this is a hot update because the number of tuples updated is 1 and the number of hot is 1. So we know that's all good. Now here's a different update where I'm updating my last updated, which does have an index. And what we see is that we did 2 updates, but we only did 1 hot. So essentially this was not a hot update, and that was the one that was very expensive. And this is the result of those changes. So now we see in yellow what the reduced index buys us. We get a much more stable run. So we have less randomness, right? And I ran this actually for much longer, and it really just sits right around 20,000 TP or inserts per second for days almost. So this is a much more effective thing. By just removing a couple indexes, we got much better results than all the parameter tuning and all the other work we did. And of course, on an update side, because we got rid of that one non-hot update, we see a doubling of our performance on the index or on by removing that hot update or removing the non-hot update. So let's go back to our table again, and let's look at some other pieces. So remember that first column that I showed you, which was the primary key, which is a UUID, and that's completely random. Well, what could we do about that? Even if you wanted to use UUIDs because you like them, this is going to cause you problems because it is fully random. So what we really want to do is we don't really want fully random. We want something that's constrained. We want something that's working over on the right side of our tree to keep the number of blocks touched smaller. So we really want something that behaves like this, where if you insert 172, it's sort of on that right side. If you insert 199, again, you're only touching a couple of blocks, right? 161, 168. None of those are causing a lot more activity, which means you have a lot less full page writes than you did if you were just doing the random thing. So how do you go about doing this? One technique that we came up with a long time ago was you can prefix your UUID with something like a date, because the date is always going to move to the right on an index, and you can choose how much precision to put on the date for how far you want it to be at the right and how many blocks you basically want to be touching. So if you have more precision, you basically are going to be less blocks, but you might have contention on those far right leaf nodes of the B tree. So that's definitely could cause a problem. But you can dial that in basically to your rate. So what I did was I changed, this original, we removed those indexes. We removed another index on this varchar, removed another random index on that one, and then we made the UUID non-random. And we made it right-leaning by adding the date to it. And this is what we get as a result. So you can see in the black there, essentially, we're now getting a super consistent run, right? That is essentially never going to have a dip because it's not doing much random work anymore. It's essentially all right-leaning, which means we have very few full page writes. We'll only, massive reduction in those numbers. Now, we see a slight increase on the number of, on the update side. And there's probably some tuning I could have done here to get that to be a better number, but mostly it's about stability on this workload that I wanted to kind of show. Now, one of the other things that's really important with Postgres is vacuuming. Now, everybody knows that you need to vacuum because you want to not run out of space on your system, and you need to vacuum because you don't want to have transaction ID wraparound. But you also need to vacuum for performance. And here's why. Let's say we have 6 tuples sitting in a block, right? And we go and update them. So the gray is sort of the old one now, and the blue is the new one, right? So it's going to end up in a new block. And so as we go, we're sitting there doing that. That's all fine, right? But let's say we fill up this whole second block with some more rows. Okay, good. Now, if we go vacuum, right, what's going to happen is, assuming there's no long-running transactions, we're going to remove those first 2 tuples and make space in the block, right? And so then when we go and update tuple 3, we're going to go back into that same block. Now, remember what I said about hot updates? One of the things that we need is to be able to do this kind of thing to get hot updates to work, right? And so that continues to happen, and we've only touched 2 blocks here. On the other hand, if we do the exact same thing and we don't run vacuum, when we go update tuple 3, notice we're now touching a new block, right? And if it's the first time since we've checkpointed, we're going to have another full page write. Not to mention, we're going to have the problem of not having a hot update. So this is going to cause a lot more performance issues. And so, you can just continue to see that without vacuuming, performance gets worse. So more blocks, more cache misses, right? Because you've got to have more memory to hold this extra space. No hot updates, more full page writes. And this is what it looks like in practice. So this, again, is another update graph. This one's run for much longer. So now you can see that this is like 20 hours. The red line is sort of just to show you what we'd hope to get for performance. The little yellow ones you can see moving up and down, and I'm kind of zoomed in on this, so it's not actually that bad. And the brown line is the moving average. So we see over time, essentially, that it does dip down quite substantially. Now you can imagine if you kept this running for days without vacuuming, that you'd start to see significant performance changes to your system if you're not vacuuming often enough. So one of the things I tell everyone, turn on vacuum logging, and then watch as it's vacuuming tables, making sure that it's getting around to the table on a regular basis and keeping them clean, right? And that way you won't have these problems. So one of the other things to think about is about how to improve specific workloads. So let's say you had an insert-only workload where essentially you're just adding more and more rows to the heap, right? And you're just adding new heap pages, and then once they fill up, you go and get another heap page, right? And if you have either no indexes or indexes that are right-leaning, in that, again, you're not going to be touching random pages. And if you have this kind of workload, and you don't have long-running transactions, one of the things that you can think about doing is actually vacuuming in memory. So how does that work? So let's go back and look at the same diagram I had before, where we have the block in memory and we have our wall. So we start doing changes, let's say inserts in this block, right? So we're slowly filling this block up, and then we're done with the block, and then at some point we checkpoint, right? And we're going to write that block out as a data file, and we're going to archive it. So that's all good, but guess what? That block's not frozen. So at some point you're going to have to vacuum that, right? So when the vacuum actually runs, it's going to pull that block back in, could be from cache, might be from disk, right? And then it's going to vacuum it and then eject it. And when it does that, you're going to get a full page into the wall stream again, right? So this is going to, again, be very expensive. And you have to re-checkpoint that page, right? So you ended up writing the page twice through checkpoint, twice through the wall stream, right? And you had to read it. So this is very expensive. If we vacuum in memory, on the other hand, we end up with the exact same, filling the block up, but then we do that vacuum in memory. And if we do that before the checkpoint happens, what happens is we only checkpoint the block out once. And we end up with no full page ending up in the wall stream. So this is essentially at least half the cost, if not more, than doing it the other way. And we end up with a block that's frozen right off the bat. So if you're doing this big load, you don't have to worry about, oh, well, the age of my tables keeps going up. So how can you do this? Well, one of the things you'd want to do is make sure your checkpoint timeout is set kind of high, because you want to be able to do this vacuuming in between the checkpoints, right? And one of the nice things about Postgres that most people know but I think sometimes forget is that you can set vacuum settings per table, right? So you can go set stuff like the max freeze age and other related parameters on a particular table so that it will vacuum in memory. So you can look at how many transaction IDs you're basically generating, what the age of that table is, and look at how long you're checkpointing, and then you can set your parameters correctly so that you can actually get it to vacuum in memory. So I ran this test just manually. If I vacuum in memory and I get that done before I checkpoint, so this is, load a bunch of data, run the vacuum, then essentially the vacuum takes 3.5 seconds, which is pretty good because this was, I think I was doing 25,000 rows per second for 10 minutes. So that's actually a lot of data to basically vacuum in 3.5 seconds. Now, when I vacuumed in memory, so after a checkpoint, so this time I loaded the data up, did a checkpoint, then did the vacuum command, it takes 84 seconds. Now, that doesn't mean your system's completely busy, but that just shows you the difference in the amount of work that has to be done between those two things, right? And then to show you what happens when it actually has to load from disk, I basically cleared the cache and cleared the page cache and did the exact same thing. Then it takes 165 seconds. So, I mean, if you're running a system, which one would you rather have? Would you rather have 3.5 seconds or 165, right? Obviously you'd like the one that is in memory. So that's, this is very specific, but it does show you how you can work with your workload to optimize these settings to get something that works much better. Now, the reason why I'm going to talk about Aurora Postgres is it's not generic Postgres, it's our version, but a lot of this stuff that I've talked about is things that came out of our work here that we looked at on ways to improve because of the challenges of doing all this tuning. And one of the things that's different about Aurora Postgres is it's a log-based system. So we have no checkpoints, we have no full page writes, and no log buffer. Now, what does that mean in practice? What that means is, like, if we go back to our log buffer example, and we have our queued work, goes into the log on Postgres, so I'll sort of fast forward through this since we've covered it. We see this stop and go motion, right? On Aurora, there is no log buffer. When work comes in, it can immediately be sent to storage. And it can be completely out of order, and what we do in Aurora is we track if we've gotten durability on those items. So it's a 4 of 6 commit system, so we need 4 acknowledgements. So if you can see that example, we have A, B, C, D, all these different items. So over time, they'll be acknowledged as durable. So for example, A there is now durable in 2 places, C is only durable in 1. Once we get to 4 durable acknowledgements, we can say it's done. Now, C's at 4, but it can't be acknowledged as done because we do need strict ordering, so we need to wait for B and everybody to get done. But you can see the difference here is that there is nothing that blocks us from having high concurrency because there's no single log buffer. The other thing that's different, because we don't have full page writes, is how writing works. Again, in Postgres, we have that same thing where full pages are emitted to the log stream after a checkpoint. So, this causes a lot of work. Checkpoints, wall, archiving, all that. On Aurora, what we have is that block in memory essentially gets the updates, and we send those as log vectors to Aurora storage. And that's it. It doesn't matter if it's, there is no before or after a checkpoint because we don't have checkpoints. So that reduces greatly the amount of work that has to be done, especially if you have a lot of indexes. So what does that look like from a practical perspective? So this now, the brown line at the top, is the Aurora Postgres. Now, remember that this is a 3AZ 6-way replicated system versus I'm comparing it currently against things that are not replicated. So you could say, well, it's basically about the same as the black line where we optimized out all kind of the indexes and we got rid of the randomness. It's pretty similar, right? And that's true. But if you couldn't make those changes to your application and you needed all those indexes, what you see is a difference between something that's doing 7,000 TPS and 26,000, right? So we didn't have to go tune the Aurora Postgres workload at all to get it to perform pretty well. And on updates, it's even more dramatic. Again, in the brown, we see that we're getting like 17,000 TPS as opposed to the 3,000 that we were getting on the base system. Again, you can tune Postgres to do quite well, but you have to spend more time in it. So, it's just an interesting thing. When you change some of these features, you can get some dramatic results. So, with that, I'm going to wrap it up and open it up for any questions. Sorry, can you repeat your question? Log. Oh, if you use unlogged, yes. So the question is, if you use unlogged feature, then you get to skip a lot of this as well. And that is correct, yes. It all depends on, again, what you're doing from a recovery perspective and, if you're replicating, whether you need those things to be logged as well. Darren? Yeah?
Seems like using the non-random UID gives you more consistent write throughput, but would you benchmark using a serial primary key instead? When would you choose one or the other?
Sure. So the question is using the non-random GUID versus serial. They are very similar. Some companies dislike sequences, right? And so they've kind of go with GUIDs. So I show that example to show that you can have sort of this thing that's fully random from a not needing or requiring a sequence, but still get the performance the same as you would get from serial. So you would see the same performance if I would have just replaced it with a regular sequenced ID. Other questions?
When using Aurora, can you do point-in-time recovery the same way with the normal implementation?
Yeah, so the question is, on Aurora, can you do point-in-time recovery the same way as standard Postgres? Yes. So Aurora has the standard roll right to, within a second of, when you did something. So yeah, it's exactly the same. Other questions? Yes?
So is there a catch in the sense that, like, does it affect the read throughput when you have concurrently write workloads?
For,
You just analyze the write workload, so you're continuously writing versus workload which is read plus write?
in just general Postgres or Aurora, I guess is.
Comparison of Aurora versus Postgres
Okay.
and the read plus write workload.
So the question is really about if you have a read plus write workload, how does that change compared to what I showed? It doesn't actually really change much. So both Aurora and regular Postgres, if the block's not in memory, it gets read. And that's still getting read as a block from both systems, right? If they're in memory, it's exactly the same. They're still just blocks in memory. So none of that has changed at all. It's just really, changing the write path, which is, so Aurora is absolutely no faster reading, out of memory than Postgres is. Postgres does a great job at that. Aurora does the exact same thing, right? It's only to get, to enable higher write workloads did, some of these changes make sense. Yes? The question is, what is the recovery time in Aurora compared to regular Postgres? So this is another is a great question, and I have a slide from another deck I could have shown. But what we see with Aurora is that because it's continuously recovering on the storage layer, there is no recovery that has to happen on a crash. So when you crash, it's about 2 to 3 seconds, no matter what write workload level you're doing. So I actually have one where I show, Postgres running and getting about 90 seconds recovery versus about 3 for Aurora. So you don't have to make that trade-off of do I want high throughput or do I want quick recovery? Other questions? What else? Oh, sorry. Oh, there you are. Sorry. The light's right, like. Go.
What exactly is the storage layer for Aurora? Is it something proprietary or is it just pretty basic?
Yeah, the question is, what is the storage layer for Aurora? It is a proprietary system. I mean, in that we've built a system of storage. The interesting thing is it's not really your typical storage. It's got parts of the database in it, right? It's taking the log vectors and doing recovery to make blocks and the storage layer. There's also a lot of other things about having the 6-way replication, being able to catch up, do repair, and all that stuff. It's like a whole nother talk. I'll probably be giving it reInvent. Yeah, it is specific to ours, which is why it doesn't make any sense to open source it because it only works in the Postgres piece of it because it doesn't actually work with anything but our storage layer. The question is the storage layer shared between Aurora MySQL and Aurora Postgres? Yeah, it's the same storage system. Obviously, they understand different things for each of the engines, but yeah, it's a shared component for us. Cool. Any other questions? Okay, yeah.
Your presentation, would you say, given the benchmarks that you've shown
Right.
here, is it more applicable to a highly transactional system as opposed to a data warehouse? And could you speak a little bit to how a data warehouse tuning arrangement might be different if data is processed in
Sure.
sets
Yeah.
and constant?
Yeah, so the question is really about, is this more applicable to sort of OLTP versus data warehousing? Yes, I mostly spend a majority of my time thinking about OLTP, so that's kind of the focus for the talk. But some of the things are applicable. For example, like the vacuuming in memory is one where it doesn't actually matter how you load the data. At some point, you need to vacuum freeze those blocks, right? And if you can do that before it gets down to disk, you get the savings that I had in the slide, right? But the things like full page writes, if you're only ever doing, inserts into a table that, basically doesn't have a lot of indexes, most of those full page write problems probably won't exist in a data warehouse, right? But some of the other things I was talking about throughput really is about trying to get the system so that moving the maximum amount of data through that log buffer as quickly as possible is still sort of applicable in a data warehousing sense. But this is, I think, from a talk perspective, a lot of the challenges really are around those random indexes in an OLTP situation. Yes?
As you were digging into trying to investigate your OLTP performance, you were showing some log dumps, and then you also sort of showed some columns
Yep.
for the full page writes. Are there any other good indicators people can kind of look at?
Yeah. You would ask me this, wouldn't you? So one of the challenges as I was writing this talk and realizing that there are no way to see full page writes in Postgres at the moment except for by dumping the logs. Which, guess what? I run a managed database service that doesn't allow you to do that. So that's kind of unfortunate, right? Which is why my colleague asking me this question is quite humorous. Yeah, so it's definitely one of those things that I think we'll look at, maybe adding something to do that, because I do think this is actually a major, kind of performance changer, right, about how much full page writes are going on. And the fact that you essentially have to do PGX log dump to figure out if you're doing full page writes is kind of bad, right? Versus some of the other work, like I was showing, like hot updates, there's a nice metric that you can easily look at, right? So I would expect something like that to be, something.
Actually, I wasn't thinking of the full page rates. I was just thinking of performance views in general.
Oh.
There's a lot of good information in there. And just I wondered if there are any that you would just kind of highlight that are kind of good ones to kind of watch.
Yeah, there's lots. Yeah. Other questions? Okay. I think if we have any other questions about the talk, RDS in general, Aurora, we'll be at our booth for the rest of the day. So we got a team here. So if you want to ask any other questions, feel free to stop by. Thank you very much.